1 light year. It sounds almost modest. Astronomers toss the phrase around like pocket change. The nearest star is 4.2 light years away. The Milky Way is 100,000 light years across. Compared with those numbers, 1 light year barely registers. But tonight, we are not going to talk about 1 light year as a measurement on a chart. We are going to send a spacecraft across it. And when you do that, when you replace the speed of light with the speed of an actual machine built by human hands, 1 light year stops being a unit and becomes an ordeal. A crossing so long that communication fails, power fades, systems age beyond recognition, and the destination is still nowhere close to another star. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Are you comfortable? Let's begin. 1 light year. Say it out loud and it sounds almost trivial. Astronomers use the term the way you might use the word block or mile, a casual unit for measuring cosmic real estate. The nearest star beyond our own is about 4.2 light years away. The Milky Way stretches roughly 100,000 light years from edge to edge. The Andromeda galaxy sits approximately 2.5 million light years from here. On those scales, 1 light year barely registers. It is a rounding error on the map of the cosmos, a single step in a journey measured in millions. But that impression is wrong. It is profoundly, dangerously wrong. And the reason it is wrong has nothing to do with astronomy. It has everything to do with speed. A light year is not a unit of time. This is the first misunderstanding, and it is remarkably common. People hear the word year inside light year and assume it describes a duration. It does not. A light year is a unit of distance. It is the distance that light travels through a vacuum in 1 Julian year, which is 365.25 days. The International Astronomical Union adopted this definition, and it gives us a very precise number. Light moves at 186,000 miles per second. That is 299,792 kilometers per second. At that velocity, light could circle the entire Earth more than 7 times in a single second. In about 1.3 seconds, it crosses the distance from the Earth to the Moon. In approximately 8 minutes, it covers the 93 million miles between the Earth and the Sun. In 1 full year, moving at that constant, unvarying speed, it covers approximately 5.88 trillion miles. In metric terms, that is 9.46 trillion kilometers. Write it out and the number is almost absurd. 5,880 billion miles. That distance, that specific stretch of emptiness, is 1 light year. When astronomers say that something is 1 light year away, they are describing a distance so large that even light, the fastest phenomenon in the known universe, requires 12 full months to cross it. Nothing known to physics moves faster. Not particles, not gravitational waves in any practical sense of outrunning light. Not information. The speed of light is not merely very fast. It is the absolute upper limit on how quickly anything can travel through space. Einstein's special relativity does not treat this as a guideline. It treats it as a law. And even at that ultimate speed, 1 light year takes a year. So here is the question that changes everything. What happens when you remove light from the equation? What happens when you replace the photon with a spacecraft? Not a theoretical spacecraft. Not a concept sketch in a physics textbook. A real machine built by real engineers, launched from Earth with real propulsion. What does 1 light-year look like when you measure it in hardware and fuel and human time? The answer is where the story begins. The fastest object humanity has ever sent into interstellar space is Voyager 1. It launched from Cape Canaveral on September 5th, 1977, aboard a Titan IIIe Centaur rocket. Its primary mission was to study Jupiter and Saturn, and it performed that mission brilliantly, returning images and data that transformed our understanding of both planetary systems. After completing its final planetary flyby at Saturn in November of 1980, Voyager 1 was directed onto a trajectory that would carry it out of the solar system entirely. It has been traveling outward ever since, nearly 50 years of continuous flight. As of 2026, Voyager 1 is approximately 15.8 billion miles from Earth. That is roughly 170 astronomical units, where 1 astronomical unit is the average distance from the Earth to the Sun. It is the most distant human-made object in existence. In August of 2012, it crossed the heliopause, the boundary where the solar wind from our Sun gives way to the interstellar medium, the thin gas and dust that fills the space between the stars. Voyager 1 is, by any meaningful definition, in interstellar space, and it is approaching a milestone that puts everything into perspective. In late 2026, Voyager 1 will reach 1 light day from Earth. A light day is the distance light travels in 24 hours, approximately 16 billion miles or 26 billion kilometers. When Voyager 1 crosses that threshold, a radio signal sent from Earth will take a full 24 hours to reach the spacecraft. A command sent in the morning will arrive the next morning. A reply, if one comes, will not return for another 24 hours after that. A 2-day round trip for a single exchange of information, traveling at the speed of light, 1 light day. After nearly 50 years, Voyager 1 moves at approximately 38,000 miles per hour. That is about 17 kilometers per second. In human terms, this is extraordinarily fast. At that speed, you could cross the continental United States from New York to Los Angeles in roughly 4 minutes. You could reach the moon in about 6 hours. Mars, depending on where it sits in its orbit, would be reachable in a few months. These are impressive numbers. They represent the pinnacle of what 1970s propulsion technology could achieve with the help of gravitational slingshots around Jupiter and Saturn. But a light year is not the moon. It is not Mars. It is not even the outer boundary of the solar system. A light year is 5.88 trillion miles, and at 38,000 miles per hour, without any acceleration or deceleration, maintaining that speed perfectly across the entire distance, the crossing takes approximately 17,600 years. 17,600 years. The entirety of recorded human history, every empire, every civilization, every language ever spoken, every city ever built, every war ever fought, stretches back roughly 5,000 years. The oldest known writing, Sumerian cuneiform, dates to about 3,100 years before the Common Era. Voyager 1 would need more than 3 times the total span of recorded civilization to travel 1 single light year. The spacecraft that has been flying longer and farther than any machine ever built by human hands would not reach the 1 light year mark for another 17 millennia. If it had launched at the dawn of agriculture, roughly 10,000 years before the present, it would still be only just past the halfway point. And this is not a hypothetical. This is the current reality. This is the actual performance of our most successful interstellar probe, traveling at its actual speed, measured against the actual distance of 1 light year. The numbers are not estimates or projections, they are arithmetic. Now, Voyager 1 is not the fastest spacecraft humanity has ever built. That distinction belongs to the Parker Solar Probe, launched by NASA in August of 2018 to study the outer corona of the Sun. The Parker Solar Probe uses a series of gravity assists from Venus to tighten its orbit closer and closer to the solar surface, and during its closest approaches, it reaches speeds of approximately 430,000 miles per hour. That is roughly 692,000 kilometers per hour. It is the fastest speed any human-made object has ever achieved, more than 11 times faster than Voyager 1. At that velocity, you could travel from New York to Los Angeles in approximately 20 seconds. At 430,000 miles per hour, 1 light year takes about 1,560 years. That is a dramatic improvement over Voyager 1. But 1,560 years is still enormous. The Western Roman Empire was in its final years about 1,560 years before the present day. If the Parker Solar Probe had somehow launched at its maximum velocity from Rome during those last years of the Western Empire, it will be reaching the 1 light year mark roughly now in the 21st century. And the Parker Solar Probe only achieves that speed during its closest passes to the Sun, when solar gravity accelerates it to maximum velocity. In open interstellar space, far from any star or planet massive enough to provide gravitational acceleration, it would be traveling much slower. The peak speed is a snapshot, not a cruise velocity. These are the numbers for machines that actually exist, not proposals, not concepts on whiteboards, real spacecraft, built and launched, currently flying, and even the best of them would require centuries or millennia to cross a single light year. So the obvious question is whether faster machines could close the gap. The answer is yes, in theory, but each theoretical option carries its own enormous set of unsolved problems. Nuclear thermal propulsion is the closest to existing technology. The concept is straightforward. You heat a propellant, typically hydrogen, by passing it through a nuclear fission reactor. The superheated hydrogen expands and is expelled through a nozzle, producing thrust. The specific impulse, the measure of how efficiently a rocket uses its propellant, is roughly twice that of the best chemical rockets. The United States tested nuclear thermal engines on the ground during the NERVA program in the 1960s, and the results were promising. The engines worked, but twice the efficiency of a chemical rocket is still profoundly inadequate for interstellar distances. A nuclear thermal spacecraft might reach velocities of 50,000 to 100,000 miles per hour. At 100,000 miles per hour, 1 light year takes approximately 6,700 years. Better than Voyager 1, but still measured in millennia. Nuclear pulse propulsion is a more radical concept. Project Orion, studied by the United States in the late 1950s and early 1960s, proposed detonating nuclear warheads behind a massive pusher plate mounted on the rear of the spacecraft. Each detonation would produce a shock wave. The pusher plate, connected to the ship by enormous shock absorbers, would absorb the impulse and accelerate the vehicle forward. Repeat the process hundreds or thousands of times, and the spacecraft builds velocity incrementally, explosion by explosion. The physics is sound. Computer simulations and engineering analyses conducted during the Orion study suggested that a sufficiently large vehicle could reach several percent of the speed of light. At 1% of light speed, approximately 6.7 million miles per hour, 1 light year takes 100 years. At 3%, about 33 years. At 5%, 20 years. These are the first numbers that begin to sound like durations a human institution might endure. Though even a century is far longer than any space mission ever attempted. But Project Orion was never built. The Partial Test Ban Treaty of 1963 prohibited nuclear weapons detonations in space, which effectively ended any near-term possibility of launching an Orion vehicle. The environmental consequences of detonating nuclear warheads in the atmosphere during the launch phase were also unacceptable. And the political reality of building a spacecraft powered by thousands of nuclear weapons was simply impossible to navigate in any era. The engineering was credible, the politics were not. The concept remains theoretically valid, but practically dormant. Fusion propulsion occupies the next tier of ambition. Fusion is the process that powers the sun, combining light atomic nuclei, typically isotopes of hydrogen, into heavier elements and releasing enormous energy in the process. A fusion drive could theoretically achieve exhaust velocities far beyond any fission system, potentially pushing a spacecraft to 5 or even 10% of light speed. At 10% of light speed, approximately 67 million miles per hour, 1 light year takes 10 years, a decade. That is a number a human crew could theoretically survive, provided everything else about the mission worked. But controlled fusion remains one of the great unsolved engineering problems of our civilization. After more than 70 years of research and tens of billions of dollars in combined global investment, no facility on Earth has achieved sustained net positive fusion energy output, meaning more energy coming out of the reaction than going in to sustain it. Experimental reactors like ITER, currently under construction in France, may demonstrate net positive fusion in the coming years. But even that milestone is far removed from building a compact, reliable fusion rocket engine capable of operating continuously for years in the vacuum of deep space. The timeline for practical fusion propulsion is measured in decades at minimum. Many physicists would say it is measured in generations. Antimatter propulsion represents the absolute theoretical ceiling of chemical and nuclear energy. When a particle of matter encounters its corresponding antiparticle, both are annihilated entirely, and their combined mass is converted into energy according to Einstein's equation. The conversion is 100% efficient. Nothing in known physics extracts more energy from a given mass. A few kilograms of antimatter could, in principle, accelerate a spacecraft to a substantial fraction of light speed. The problems are production and storage. Antimatter does not exist in accessible natural quantities anywhere in the solar system. It must be manufactured in particle accelerators, one atom at a time, through collisions that produce particle-antiparticle pairs. The total amount of antimatter ever produced on Earth, across all laboratories and all experiments combined, is less than 20 nanograms, 20 billionths of a gram. Producing a single gram of antimatter using current methods would cost trillions of dollars and take longer than any institution would fund. Storing it is equally daunting. Antimatter cannot contact any ordinary matter without annihilating instantly. Containment requires magnetic traps operating with perfect reliability for the entire duration of the mission. One failure, even momentary, and the fuel supply detonates. A single kilogram of antimatter annihilating releases energy equivalent to approximately 43 megatons of TNT, approaching the yield of the largest nuclear weapon ever tested. Antimatter propulsion is not an engineering program. It is an aspiration waiting for physics we do not yet have. Laser sail propulsion offers a different approach entirely. Instead of carrying fuel, you leave the energy source behind. A ground-based or space-based laser array fires a concentrated beam of light at a highly reflective sail attached to the spacecraft. Photons carry momentum, and when they reflect off the sail, they transfer that momentum, pushing the craft forward. No onboard fuel is needed. All the energy stays on the ground. The Breakthrough Starshot initiative, announced in 2016 by science philanthropist Yuri Milner and the late Stephen Hawking, proposed exactly this concept. A laser array producing approximately 100 gigawatts of power would accelerate a gram-scale spacecraft, roughly the mass of a paperclip, to 20% of the speed of light. At that speed, 1 light year would take only 5 years, but the spacecraft would weigh about a gram. It could carry a few cameras and perhaps a basic spectrometer, nothing more. It could not slow down at the destination. It would scream through whatever it passed at 60 million meters per second, snapping pictures for hours at most, before continuing into the void forever. Even this minimal concept faces staggering challenges. The laser array would need to focus a beam of extraordinary intensity onto a sail that is already accelerating away from Earth at thousands of kilometers per second. The pointing precision required is beyond anything current optical systems can achieve. The cost of the array alone would run into tens of billions of dollars. And a 2025 investigation found that the Breakthrough Starshot initiative had largely stalled, with less than $10 million spent over 9 years, key research grants ending, and organized meetings ceasing. The concept helped normalize the idea that interstellar travel could be a legitimate engineering goal, but the hardware remains far from reality. Research on light sail materials continues independently. In 2025, a team published work in Nature Communications on pentagonal photonic crystal reflectors, demonstrating a roughly 9,000-fold reduction in fabrication costs for ultra-thin sails with billions of nanoscale features. At Caltech, researchers made the first experimental measurements of direct radiation pressure on miniature light sails in the laboratory. The physics of light-driven propulsion is real. The gap between laboratory demonstrations and an interstellar mission is still enormous. So let us lay the numbers side by side. 1 light year, 5.88 trillion miles. The distance light crosses in 12 months. At Voyager 1 speed, that crossing takes approximately 17,600 years. At the Parker Solar Probe's peak velocity, approximately 1,560 years. At 1% of light speed, 100 years. At 5% of light speed, 20 years. At 10%, 10 years. At 20%, 5 years. These numbers span a range from the flatly impossible to the barely conceivable, and every single one of them, from the slowest to the fastest, describes a journey longer than any space mission ever completed. The longest crewed spaceflight in history was cosmonaut Valery Polyakov's 437 consecutive days aboard the Mir space station, completed in March of 1995. 14.5 months. That is the human endurance record for continuous time in space. The International Space Station has been continuously occupied since November of the year 2000, roughly 26 years of unbroken habitation. But the station sits in low Earth orbit, 250 miles above the surface, where resupply missions arrive every few weeks, where the crew can be evacuated in hours if something goes wrong, where mission control in Houston is a few seconds away by radio. 1 light year at 10% of light speed, a velocity that requires propulsion technology we do not yet possess, is 10 years, more than 7 times longer than the longest individual human spaceflight ever attempted. And it would unfold not in the relative safety of low Earth orbit, but in deep interstellar space, far from any star, with no resupply, no rescue, and a communication delay measured not in seconds, but in months or years. This is what happens when you translate 1 light year from a number on a chart into a journey through physical space. The distance does not change. It is always 5.88 trillion miles, but the meaning transforms completely. For light, 1 light year is a year of effortless travel at the maximum speed the universe permits. For a spacecraft, it is a crossing measured in decades, centuries, or millennia, depending entirely on how fast the machine can go. And during every single one of those years, every month, every day, the spacecraft is alone. It carries everything it needs, or it does not survive. There is no harbor at the halfway point, no supply depot, no rescue mission that could arrive in time to matter. The ship either works for the full duration of the crossing, or it does not work at all. 1 light year is not a distance you fly, it is a distance you endure. And endurance depends on far more than speed. Because a spacecraft crossing 1 light year is not gliding through emptiness. It is moving through the interstellar medium, and the interstellar medium is not empty. It is thin. It is cold. It is dark. But it contains gas. It contains dust. And it contains radiation that does not stop at the hole. Every mile of that 5.88 trillion mile crossing is made of something. And that something accumulates. Quietly. Steadily. Mile after mile. Year after year. Until it becomes the real story of the journey. The distance is 5.88 trillion miles. What matters now is what those miles are made of. There is a word people use when they describe interstellar space. They call it empty. And it is easy to see why. If you could look out the window of a spacecraft 1 light year from Earth, you would see nothing with your naked eyes except stars. No planets nearby, no moons, no asteroids drifting past, no glowing nebulae close enough to resolve, just pinpoints of light scattered across an absolute blackness that extends in every direction without limit. The same stars you might have seen from Earth, shifted slightly by parallax but otherwise indistinguishable from the familiar night sky. You could press your face to the glass and search for anything, any feature, any landmark, any point of reference between you and the infinite dark, and you would find nothing. But interstellar space is not empty. It never has been. And the difference between what your eyes would tell you and what your instruments would measure is the difference between a journey that sounds safe and one that could destroy the spacecraft making it. The space between the stars is filled with what astronomers call the interstellar medium. It is an extraordinarily thin soup of gas and dust spread across the galaxy, threaded with magnetic fields and permeated by high-energy radiation. In some regions, it is denser. In others, it is thinner. But it is never truly absent. Everywhere you travel between the stars, you're moving through material, and that material interacts with anything passing through it. The interaction is subtle at low speeds. At the velocities required for interstellar travel, it becomes serious. The dominant component of the interstellar medium is hydrogen. Roughly 90% of the atoms in interstellar space are hydrogen, the simplest element, a single proton orbited by a single electron. Another 9% or so is helium. The remaining fraction, less than 1%, consists of heavier elements: carbon, oxygen, nitrogen, silicon, iron, magnesium, and others forged in the cores of ancient stars and scattered into space by supernova explosions billions of years ago. The density of this gas varies enormously depending on where you are. In the densest molecular clouds, where new stars are actively forming, hydrogen packs in at thousands or even millions of atoms per cubic centimeter. These are the stellar nurseries, the birthplaces of suns, and they are spectacular concentrations by interstellar standards. But a spacecraft heading outward from the solar system is not traveling through a molecular cloud. It is traveling through the diffuse interstellar medium, and out here the density drops to something almost incomprehensibly thin. In the general neighborhood of the Sun, the interstellar medium contains roughly 1 atom per cubic centimeter. To understand how sparse that is, consider that the air you are breathing right now, the ordinary atmosphere at sea level, contains approximately 25 quintillion molecules per cubic centimeter. That is 25 followed by 18 zeros. The interstellar medium contains 1. If you filled an Olympic swimming pool with interstellar medium and somehow compressed it to examine the total contents, the amount of actual matter would be less than a single grain of sand. This is the substance the spacecraft is traveling through. It sounds negligible. It almost sounds like it should not matter at all. But over trillions of miles and years of travel, even something this thin accumulates. The solar system does not sit in a perfectly average patch of the galaxy. It is currently passing through a structure called the local interstellar cloud, sometimes referred to as the local fluff. This cloud is a region of warm, partially ionized gas about 30 light years across, with a temperature of roughly 6,000 to 7,000 Kelvin. That temperature sounds high, and it is high compared to colder interstellar regions, but in a gas this thin, temperature refers to how fast the individual atoms are moving, not how much heat you would feel. You could pass through gas at 7,000 Kelvin and barely register it thermally, because there are so few particles that the total energy transferred to a surface is minuscule. The local interstellar cloud is warm in the atomic sense, but carries almost no heat in the everyday sense. A 2025 study using high-resolution ultraviolet spectra from the Hubble Space Telescope mapped the structure of the local interstellar medium in new detail, identifying multiple discrete clouds and refining the boundaries of known structures. The picture that emerges is not one of uniform emptiness, but of a patchwork of clouds, each with its own velocity, temperature, and composition, drifting through the galaxy on timescales of millions of years. Beyond the local interstellar cloud lies the G cloud, another warm, diffuse structure, and farther still are cooler, denser clouds with different chemical signatures. A spacecraft crossing 1 light year from the Sun would likely pass through parts of the local interstellar cloud and potentially encounter the edges of neighboring clouds with different properties. We know what this transition feels like because a spacecraft has already made it. When Voyager 1 crossed the heliopause in August of 2012, it did not pass through a clean boundary. There was no line in space where the solar system ended and the interstellar medium began. Instead, Voyager 1 spent months in a turbulent transitional region called the heliosheath, where the solar wind slows, compresses, and begins to mix with incoming interstellar particles. The spacecraft's instruments registered a gradual increase in galactic cosmic ray intensity, and a corresponding decline in solar energetic particles. The magnetic field direction shifted. The density of the plasma surrounding the spacecraft changed. For weeks, the data were ambiguous. Engineers and scientists debated whether the crossing had actually occurred, or whether Voyager 1 was passing through a transient structure near the boundary. It was only when the Plasma Wave Science instrument detected a sharp and sustained increase in plasma density, consistent with the denser interstellar medium rather than the thinner solar wind, that the team confirmed the crossing. Voyager 1 was outside. It had left the heliosphere, the vast bubble of charged particles inflated by the sun's output, and entered the interstellar medium that fills the space between the stars. The transition mattered because it changed the environment in measurable ways. Inside the heliosphere, the solar wind provides a partial shield against galactic cosmic rays. The sun's magnetic field, carried outward by the solar wind, deflects some fraction of incoming high-energy particles. It is not a strong shield, but it is not negligible. Beyond the heliopause, that shield is gone. The full flux of galactic cosmic rays reaches the spacecraft undiminished. The particle environment shifts from one dominated by the sun to one dominated by the galaxy. The plasma surrounding the spacecraft is no longer solar material flowing outward. It is interstellar material, ancient gas that has drifted between the stars for millions of years, carrying its own temperature, composition, and velocity relative to the sun. A spacecraft crossing 1 light year passes through this transition early in its journey, probably within the first few hundred astronomical units, depending on the direction of travel and the shape of the heliosphere in that direction. After the transition, the environment stabilizes into the diffuse interstellar medium described above. But stabilize is a misleading word. It suggests calm. What it actually means is that the conditions stop changing and settle into a permanent, unvarying hostility. The cosmic ray flux holds steady at its full galactic intensity. The gas density holds at roughly 1 atom per cubic centimeter. The temperature holds near the ambient value of the local cloud. And none of it improves. There is no second boundary to cross that restores protection. There is no sheltered region ahead. The spacecraft has left the last natural shield the solar system provides, and from this point forward, every mile is interstellar. But the gas is not the primary physical threat to a spacecraft. The dust is. Interstellar dust consists of tiny solid particles, typically made of silicate minerals, carbon compounds, or a combination of both. Some grains carry thin coatings of water ice or organic molecules. They are extraordinarily small. A typical interstellar dust grain measures between 1/10 of a micrometer and 1 micrometer in diameter. A micrometer is 1/1,000,000th of a meter. A human hair is roughly 70 to 100 micrometers wide. These grains are hundreds of times smaller than the width of a hair, invisible to the naked eye, and individually they carry almost no mass. A single grain might weigh 1/1,000,000th of a gram or less. At the speeds we are accustomed to, a particle this tiny would be completely harmless. Even at Voyager 1's velocity of 38,000 miles per hour, the kinetic energy of a single interstellar dust grain is negligible. You would not notice it. The spacecraft would not notice it. But the entire premise of interstellar travel depends on going much, much faster than Voyager 1. And kinetic energy does not increase proportionally with speed. It increases with the square of speed. Double the velocity and the kinetic energy quadruples. Increase the velocity by a factor of 100, and the kinetic energy increases by a factor of 10,000. At 10% of the speed of light, which is roughly the minimum velocity needed to cross 1 light year in a human lifetime, A spacecraft is traveling at approximately 67 million miles per hour. A dust grain with a mass of 1 milligram, about the weight of a small grain of table salt, striking the spacecraft at that speed carries kinetic energy equivalent to roughly 100 kilograms of TNT. That is not a metaphor. The physics is straightforward. 1/2 times the mass times the velocity squared gives you the energy, and at 10% of light speed, even a milligram becomes a weapon. A single impact would be equivalent to a rifle bullet carrying thousands of times more energy than a conventional round. It would not bounce off the hull. It would vaporize on contact, creating a superheated plasma that would excavate a crater in whatever surface it struck, melting and ejecting material in a miniature explosion. A spacecraft crossing 1 light year sweeps through an enormous volume of interstellar space. The exact number of dust grain impacts depends on the size of the spacecraft's forward cross-section, the density of the interstellar medium along its path, and the distribution of grain sizes. Detailed simulations published by researchers at Lawrence Livermore National Laboratory modeled what happens when interstellar dust grains strike a spacecraft traveling at relativistic speeds. They found that each grain deposits its energy in a long, thin, cylindrical volume inside the whole material, creating temperatures exceeding 10 million Kelvin at the point of impact. The damage radius depends on the grain size, the whole material, and whether the energy is carried away by radiation and evaporation or retained as heat in the surrounding material. For a large crewed spacecraft with a hull measured in meters of thickness, individual small grain impacts would be survivable. The crater would be tiny, the damage localized. But the problem is accumulation. Over 1 light year of travel, the spacecraft would encounter millions of individual dust grains. Most would be vanishingly small, depositing only trace amounts of energy. But the statistical tail of the distribution includes grains large enough to cause meaningful surface damage. Over enough distance, the leading face of the spacecraft erodes. The whole material is pitted, cratered, and weakened. Layer by layer, impact by impact. The forward surface degrades, and this degradation cannot be repaired from the outside during flight. Shielding strategies exist. A sacrificial bumper shield, positioned ahead of the main hull with a gap between them, can fragment incoming particles before they reach the structural hull. This is the same principle as the Whipple shield, developed in the 1940s by astronomer Fred Whipple for protecting spacecraft from micrometeoroids. The outer bumper vaporizes the incoming particle. The resulting debris cloud spreads out across the gap, distributing its energy over a wider area of the inner hull rather than concentrating it at a single point. Modern spacecraft use refined versions of this approach. A deep space vehicle designed for interstellar transit would need advanced multi-layered shielding across the entire forward-facing surface, and that shielding would need to withstand years or decades of continuous bombardment without being serviced from outside. Some researchers have proposed using electromagnetic fields to deflect charged particles before they reach the hull. If dust grains are ionized by ultraviolet radiation or by the spacecraft's own interaction with the interstellar medium, a strong magnetic field could redirect them away from the hull entirely. But not all grains are charged, and the power required to maintain a sufficiently strong magnetic field over a large enough area adds another demand to the spacecraft's already strained energy budget. Then there is the radiation. Galactic cosmic rays are high-energy particles that stream through interstellar space continuously. They are not a weather event. They are not periodic. They are a permanent, unrelenting feature of the interstellar environment. Most galactic cosmic rays are protons, roughly 85%. Another 12 to 14% are alpha particles, helium nuclei stripped of their electrons. The remaining 1 to 2% are heavier atomic nuclei, everything from carbon and oxygen up to iron and beyond, stripped bare of their electrons and accelerated to enormous energies by supernova remnants, shock waves, and other violent astrophysical processes scattered across the galaxy. The energies involved are extreme. Individual galactic cosmic ray particles carry energies ranging from millions of electron volts, abbreviated as mega electron volts, to billions of electron volts, gigaelectron volts, and in rare cases far higher. The most energetic cosmic rays detected carry as much kinetic energy as a baseball thrown hard across a playing field, concentrated into a single subatomic particle. These are the so-called ultra-high energy cosmic rays, and while they are rare, they exist, and they cannot be stopped by any practical thickness of shielding. On Earth, we are protected from galactic cosmic rays by two overlapping shields. The first is the planet's magnetic field, which deflects many charged particles before they can reach the atmosphere. The second is the atmosphere itself, a column of air equivalent to roughly 10 meters of water in shielding depth, which absorbs most of the particles that make it past the magnetic field. By the time cosmic ray interactions reach the surface, they have been degraded and scattered into secondary particles, most of which are harmless. In interstellar space, both shields are gone. There is no magnetic field. There is no atmosphere. The spacecraft hull provides some shielding, but stopping high-energy protons requires dense material, and more of it than most spacecraft designs can practically carry. Water is a moderately effective shield for certain particle types. Polyethylene performs well because of its high hydrogen content, which is efficient at absorbing neutron radiation. But galactic cosmic rays with energies in the giga-electron volt range can penetrate meters of solid material. They do not stop at the hull. They pass through the hull, through the equipment inside, through the bodies of any crew members aboard, depositing ionizing energy as they go. The biological effects of chronic cosmic ray exposure are well studied, at least in principle. Ionizing radiation damages DNA. It breaks the double helix, creates mutations, disrupts cellular repair mechanisms, and increases the risk of cancer. On the International Space Station, astronauts receive a radiation dose roughly 100 times higher than on the ground, even within the partial protection of Earth's magnetic field. On a deep space mission beyond that magnetic field, the dose rate approximately doubles, and the composition of the radiation changes. More heavy ions reach the crew, and heavy ions are especially damaging biologically because they deposit energy along a dense track through tissue, causing clustered DNA damage that is harder for cells to repair. NASA's research on space radiation for its planned missions to Mars has consistently identified galactic cosmic rays as one of the most serious health risks for long-duration spaceflight. A round-trip Mars mission would expose the crew to roughly 1 sievert of cumulative radiation, which is associated with a measurable increase in lifetime cancer risk. 1 light year of travel at any speed would expose the crew to years or decades more radiation than a Mars mission. The cumulative dose would depend on the speed of travel, faster means less time exposed, and the thickness and composition of the shielding. But under any realistic scenario, the radiation exposure across 1 light year would far exceed any dose that current health standards would permit. And cosmic rays do not only damage biological tissue, they damage electronics. When a high-energy particle strikes a semiconductor chip, it can deposit enough charge in a single transistor to flip a binary digit from 0 to 1 or 1 to 0. This is called a single event upset. In most cases, a single event upset is a momentary glitch, a bit of corrupted data that can be detected and corrected by error-checking algorithms. But in critical systems, a single event upset in the wrong register at the wrong moment can cause a command to be misinterpreted, a sensor reading to be falsified, or a system to enter an unintended state. Over years of continuous exposure, the cumulative radiation dose also degrades semiconductor materials at the structural level, increasing leakage currents, shifting voltage thresholds, and gradually reducing the reliability of every electronic component on the spacecraft. Voyager 1's engineering team experienced this directly. In late 2023, one of Voyager 1's onboard computers began sending garbled, repetitive data instead of valid telemetry. Engineers traced the fault to a single failed memory chip, likely degraded by decades of cosmic ray exposure. They devised a software workaround, relocated the affected code to a different section of memory, and transmitted the fix across more than 15 billion miles of space, where each command took nearly a full day to arrive. By April of 2024, normal communication was restored. It was a remarkable feat of remote engineering, but it also illustrated a stark reality. After roughly 47 years in space, the electronics on Voyager 1 are failing, and the cause is the relentless, invisible bombardment of cosmic radiation that has been striking the spacecraft every second of every day since it launched. A spacecraft crossing 1 light year would face this same bombardment, but for far longer. At Voyager speeds, the crossing takes thousands of years. Even at faster speeds, the exposure spans decades. Every circuit board, every memory chip, every sensor, every processor aboard the spacecraft is being irradiated continuously, and there is no way to shield it completely without adding mass that makes the spacecraft heavier, which requires more fuel, which makes it heavier still. Beyond the gas, the dust, and the radiation, there is a more fundamental feature of the environment that is easy to overlook because it has no physical substance. It is the darkness. Not the poetic darkness of a moonless night on Earth, where there is still atmosphere scattering faint starlight, still the warmth of a nearby sun below the horizon. Interstellar darkness is absolute in every direction that does not contain a star. The sun, from 1 light year away, is not a sun anymore. It is a star. A bright one, brighter than most of the stars in the sky, but a star nonetheless. A point of light with no disk, no warmth, no presence. The amount of solar energy reaching the spacecraft at a distance of 1 light year is vanishingly small. The inverse square law governs this mercilessly. At twice the distance, light intensity drops to 1/4. At 10 times the distance, 1/100th. At a light year, the sun's output is spread across such an enormous sphere that the fraction intercepted by anything as small as a spacecraft is effectively zero. Solar panels, even enormous ones, would produce no usable electricity. Solar heating, the passive warmth that keeps spacecraft components from freezing in the inner solar system, is gone. The background temperature of interstellar space is set by the cosmic microwave background radiation, the remnant glow of the Big Bang. It is approximately 2.7 Kelvin. That is 2.7 degrees above absolute zero. negative 270.45 degrees Celsius, negative 454.81 degrees Fahrenheit. At that temperature, most gases are solid. Metals become brittle, lubricants freeze, seals harden and crack. Electronics behave differently at cryogenic temperatures, with increased resistance in some materials and superconductivity in others. The spacecraft must generate all of its own heat or freeze, and there is something else the darkness conceals. There is no destination at 1 light year. This is a point that gets lost in the mathematics of speed and distance, but it is critically important. 1 light year is a measurement. It is not a place. No known star sits at exactly 1 light year from the Sun. The nearest star to our solar system, Proxima Centauri, is 4.24 light years away. The next closest, Barnard's star, is about 6 light years away. In fact, at 1 light year from the Sun, the spacecraft may not have fully left the solar system in the broadest gravitational sense. The Oort cloud, a theoretical shell of icy bodies loosely bound to the Sun by gravity, is believed to extend from roughly 2,000 astronomical units out to as far as 100,000 astronomical units or more. 1 light year is approximately 63,000 astronomical units. That places it well within the outer boundary of the Oort cloud, if the cloud extends as far as current models suggest. The spacecraft has entered the interstellar medium. It has lost the solar wind, the heliospheric shielding, the warmth of the Sun, and any practical connection to Earth. But gravitationally, it may still be inside the loosest, outermost reach of the Sun's influence, drifting through a sparse halo of ancient cometary bodies that orbit the Sun on timescales of millions of years. It has lost everything the solar system provides except the faintest claim of gravitational membership, and that claim offers nothing useful. No warmth, no shelter, no destination. Just the knowledge that the Sun's gravity, weakened to almost nothing at this distance, still technically holds a few frozen objects in orbits, so vast they barely qualify as orbits at all. A spacecraft that has travelled 1 light year from Earth has not arrived anywhere. It has not reached another star. It has not entered another solar system. It has not found a planet, a moon, a source of fuel, or a safe harbour of any kind. It is in the interstellar medium, surrounded by thin gas and faint dust, and cosmic radiation and cold and darkness, with absolutely nothing nearby except more of the same stretching ahead for trillions of additional miles. This is what separates interstellar travel from every other kind of journey humans have ever attempted. When explorers crossed oceans, there were islands along the way. Harbours, fresh water, land where you could stop and repair your ship and restock your provisions before continuing. When spacecraft travel within the solar system, there are gravitational waypoints. Planets whose gravity can be used for course corrections and speed boosts. Moons where a future mission might land and refuel. The solar system is structured. It has geography. It has options. The interstellar medium has none of that. There are no waypoints, no rest stops, no gravitational assists from objects large enough to matter. Once the spacecraft leaves the gravitational influence of the Sun, it is in a flat, featureless expanse of nearly nothing, and it stays there for the entire crossing. Every mile looks like the last. Every year feels like the one before. The environment does not change in any way a human crew could perceive without instruments. The stars drift imperceptibly over decades due to the spacecraft's changing vantage point, but the change is so slow that it would be invisible on any human timescale. Day after day, year after year, the view out the window is the same. The instruments read the same. The darkness is the same. This featurelessness deserves emphasis because it separates interstellar travel from every journey humans have ever experienced. On Earth, every landscape changes. Deserts give way to mountains, forests thin into grassland. Oceans have currents and weather and coastlines that eventually appear. Even the most monotonous ocean crossing offers daily variation in wave height, cloud cover, wind, the position of the sun in the sky, the slow rotation of constellations overhead. The human brain evolved to process these changes. It calibrates time by environmental variation. It maintains alertness through novelty. It builds an internal map of progress by noticing that something, anything, is different today than it was yesterday. A spacecraft 1 light year from Earth offers none of that. The interstellar medium does not have weather. It does not have terrain. It does not change perceptibly from 1 year to the next. The cosmic ray flux is constant. The dust density is nearly uniform over distances much smaller than a light year. The temperature does not fluctuate. There is no day cycle, no season, no landmark to confirm that the spacecraft has moved at all. If the instruments were turned off, if the crew relied only on what they could perceive through their senses, they would have no evidence that the ship was moving. They would sit in a motionless vessel surrounded by fixed stars and unchanging darkness, and nothing in their sensory experience would contradict the impression that they had stopped. The interstellar medium also carries magnetic fields. These fields are weak, measured in microgas, millions of times weaker than a refrigerator magnet, but they are structured, draped along the spiral arms of the galaxy, threaded through clouds of gas and dust, shaping the distribution of charged particles and influencing the propagation of cosmic rays. For a spacecraft with sensitive electronics or systems that depend on stable magnetic environments for navigation or data storage, even weak ambient magnetic fields over long durations represent a variable that must be accounted for. The fields are not dangerous in themselves, but they are part of the environment. Another reminder that interstellar space, however empty it looks, is not a void. It is a medium, and a medium interacts with anything moving through it. The cumulative picture is sobering. A spacecraft crossing 1 light year is not gliding through nothing. It is being sandblasted by microscopic dust grains that carry explosive energy at high speed. It is being irradiated by cosmic rays that damage both its electronics and its crew. It is losing heat to a background temperature close to absolute zero. It is flying through thin but measurable gas that, over trillions of miles, represents a meaningful amount of accumulated material sweeping across every forward-facing surface. It is navigating without landmarks, without waypoints, without any destination closer than 4 times the distance it has already covered. And it is doing all of this in darkness so complete that the sun itself has become indistinguishable from any other star in the sky. None of these threats is dramatic in the cinematic sense. There is no explosion, no asteroid hurtling toward the hole, no sudden crisis with flashing alarms and seconds to react. The hazards of the interstellar medium are slow, quiet, and cumulative. They operate on timescales of years and decades, not minutes. Dust erosion happens 1 grain at a time. Radiation damage accumulates 1 particle at a time. Heat loss is continuous and relentless. The degradation is so gradual that on any given day, nothing appears to have changed. But across the full distance of 1 light year, the accumulation is significant, And this is only the environment, the external conditions pressing inward on the whole. Inside the spacecraft, a parallel set of problems is unfolding, driven not by the interstellar medium, but by time itself. Systems age, components wear, power fades, and the ship moves further and further from the only world that knows how to fix anything that breaks. The crossing of 1 light year is made of 5.88 trillion miles of gas, dust, radiation, cold, and darkness. Every one of those miles is real. Every one of them acts on the spacecraft. And every one of them is followed by another mile exactly like it. That is the environment. That is what the ship endures. And the ship has not even begun to endure itself. Everything described so far has been external. The environment, the gas, the dust, the radiation, the cold, the darkness. These are the conditions pressing inward on the whole from outside. They are serious, they are relentless, but they are not the only threat. Inside the spacecraft, a separate category of failure is unfolding, and it has nothing to do with the interstellar medium. It has to do with time. Time is the enemy that no spacecraft was ever designed to defeat. Every machine ever built has a service life, a span of years beyond which components degrade. Systems drift out of calibration, and the probability of failure climbs from unlikely to inevitable. An automobile lasts perhaps 15 to 20 years with regular maintenance and replacement parts. A commercial aircraft is certified for roughly 20 to 30 years of structural life before fatigue sets in. A naval vessel, built to military standards with heavy-gauge steel and redundant systems, might serve 40 to 50 years before it is retired. These are the most durable machines human civilization produces. None of them last a century, and 1 light year at any speed currently achievable takes far longer than a century to cross. The spacecraft does not merely travel through the interstellar medium, it ages inside it. And the aging begins the moment the engines stop firing and the long coast begins. Start with communication, because communication is the first thing the spacecraft loses, and losing it changes everything. At the moment of launch, the spacecraft is in constant contact with Earth. Radio signals travel at the speed of light, and in the inner solar system, the delay is manageable. From low Earth orbit, the delay is a fraction of a second. From the Moon, about 1.3 seconds. From Mars at its closest approach, roughly 4 minutes one way. Even from the outer solar system, communication is feasible. When the New Horizons spacecraft flew past Pluto in July of 2015, it was approximately 3 billion miles from Earth. Radio signals took about 4.5 hours each way. Mission controllers could send a command, wait 9 hours for a round trip, and receive a response the same day. Slow by terrestrial standards, but still functional. Still a conversation, even if it moved at the pace of correspondence rather than dialogue. But as the spacecraft moves outward, the delay grows, and it grows without limit. At 1 astronomical unit from the Sun, 8 minutes. At 10 astronomical units, roughly the distance of Saturn, 80 minutes. At 100 astronomical units, the approximate distance where the solar wind gives way to the interstellar medium, about 14 hours. At 1 light day, 24 hours. And at 1 light year, the delay is exactly what the name implies. 1 year, 12 months, 365 days for a single message to travel from Earth to the spacecraft. 1 year to send a question. 1 year to receive the answer. A round-trip conversation takes 2 full years. If the spacecraft encounters a problem and transmits a distress call, The engineers on Earth will not even know about it for 12 months. Their response, however brilliant, however perfectly crafted, will not arrive at the spacecraft for another 12 months after that. 2 years between the moment the crisis begins and the moment any help, any guidance, any instruction from Earth reaches the spacecraft. And in those 2 years, the crisis has either been resolved by the crew and systems on board, or it has not. If it has not, no response from Earth will be timely enough to change the outcome. This is not merely an inconvenience, it is a fundamental transformation of the mission's architecture. Every spacecraft ever flown by NASA, the European Space Agency, or any other space agency has relied on ground-based mission control for critical decision-making. The Voyager 1 computer failure described earlier was resolved because the communication delay was still manageable, roughly 23 hours each way. Engineers had nearly a full day to wait between command and response. That was challenging but workable. At 1 light year, the same process would take 2 years. If the computer failure was causing the spacecraft to lose attitude control, to tumble slowly end over end, to point its antenna away from Earth, so that communication was no longer possible, 2 years of waiting would mean the spacecraft was already lost. The practical consequence is that a spacecraft crossing 1 light year must be capable of solving every problem it encounters entirely on its own. Every diagnosis, every repair decision, every course correction, every systems failure. It cannot phone home for help. It can't wait for instructions. It must carry within itself, within its onboard computers and its crew, if it has one, the full capability to handle anything that goes wrong. This is autonomy not as a feature, but as a survival requirement imposed by the physics of distance. To understand what that autonomy means in practice, imagine a specific scenario. A seal in the primary coolant loop of the spacecraft's fission reactor develops a slow leak. The leak is small, measurable only by a slight drop in coolant pressure over a period of weeks. The onboard monitoring system detects the anomaly and flags it. The spacecraft's diagnostic software identifies the most probable source based on sensor data and system models. An automated repair protocol is initiated, but the repair requires isolating the affected coolant section, which means temporarily reducing reactor output, which means reducing electrical power to the entire spacecraft for the duration of the repair. Reducing power means turning off non-essential systems. Heating in secondary compartments stops. Temperatures in those compartments begin to drop. If the repair takes longer than expected, if the leak is harder to isolate than the software predicted, the temperature in those compartments drops further. Components in those compartments begin to approach their lower operating limits. A backup sensor in one of the cooling compartments, itself affected by the declining temperature, begins producing erratic readings. The diagnostic software, still managing the original coolant leak, now receives conflicting data from the secondary sensor and must decide whether the new anomaly is real or an artifact of the cold. On Earth, this kind of cascading decision tree is handled by a room full of engineers with historical data, simulation tools, and the ability to confer with specialists at other facilities. They can test hypotheses and arrive at a consensus before sending a command. In interstellar space, at 1 light year from Earth, those engineers cannot participate. The spacecraft's software and crew, if there is a crew, must resolve the original leak, manage the power reduction, monitor the temperature decline, evaluate the secondary sensor anomaly, and decide how to allocate diminishing resources, all without any input from the ground. And every decision they make narrows the options available for the next decision. Fix the leak quickly and you restore power, but risk an incomplete repair. Take more time and you risk thermal damage to secondary systems. Trust the erratic sensor and you might chase a phantom problem while the real one worsens. Ignore it and you might miss a genuine second failure. This is what autonomy means across 1 light year. Not independence in the philosophical sense. Independence in the operational sense. Every crisis is local. Every solution must come from within. And the margin for error shrinks with every year of the crossing, because the systems making the decisions are themselves aging, themselves degrading, themselves subject to the same forces that created the problem in the first place. Now consider power. Every system aboard the spacecraft runs on electricity. The computers that controlled navigation, the heaters that keep electronics within operating temperature, the communication transmitter that sends data back to Earth, the sensors that monitor the spacecraft's health, the life support systems if there is a crew, all of it requires power. And power in deep space is a problem with no permanent solution. Solar panels are useless. This was established earlier, but the operational reality deserves emphasis. Even the most efficient solar panels ever manufactured produce electricity by converting sunlight into current. At 1 astronomical unit from the Sun, where Earth orbits, solar intensity is approximately 1,360 watts per square meter. At the distance of Jupiter, roughly 5 astronomical units, it drops to approximately 50 watts per square meter. At the distance of Pluto, about 40 astronomical units, it is less than 1 watt per square meter. At 1 light year, 63,241 astronomical units from the Sun, the solar flux is so close to zero that it cannot be meaningfully measured. Solar power is not an option. It has not been an option since the spacecraft passed the orbit of Jupiter. The only proven technology for generating electricity in deep space is the radioisotope thermoelectric generator. An RTG converts heat from the natural radioactive decay of plutonium-238 into electricity using devices called thermocouples. The principle is simple. Plutonium-238 is an unstable isotope that decays by emitting alpha particles, generating heat in the process. This heat is converted into an electric current by the temperature difference between the hot plutonium fuel and the cold exterior of the generator, which radiates waste heat into space. There are no moving parts, no turbines, no pumps, no combustion chambers. Just a block of radioactive material slowly decaying, and a set of thermocouples extracting useful electricity from the temperature gradient. RTGs have powered some of the most successful missions in the history of space exploration. Pioneer 10 and Pioneer 11 carried them into the outer solar system in the early 1970s. Voyager 1 and Voyager 2 have been running on RTGs since 1977. The Cassini spacecraft used them to explore Saturn for 13 years. The Curiosity and Perseverance rovers on Mars use a newer version called the multi-mission radioisotope thermoelectric generator, which produces approximately 110 watts of electrical power. RTGs are reliable, self-contained, and proven across decades of operation. They are the only power source that has ever functioned successfully in deep space for more than a few years. But they decay. That is the fundamental limitation. Plutonium-238 has a half-life of approximately 87.7 years. This means that after 87.7 years, half of the original plutonium has decayed into uranium-234 and is no longer producing heat. After another 87.7 years, half of the remainder has decayed. The power output drops continuously, year after year, following an exponential curve that cannot be slowed, paused, or reversed. When Voyager 1 launched in 1977, its 3 RTGs produced a combined output of approximately 470 watts of electrical power. By 2026, nearly 50 years later, they produce roughly 249 watts. That is a loss of nearly half the original output, and it is enough to force agonizing decisions about which instruments to keep running and which to shut down forever. In 2025, the Voyager team switched off the cosmic ray subsystem, the very instrument that had confirmed the spacecraft's crossing into interstellar space in 2012, purely to conserve power. Each shutdown buys another year or two of life for the remaining systems. NASA estimates that Voyager 1 will be unable to power any science instruments by approximately 2030, after which the spacecraft will fall silent. It will continue drifting through interstellar space forever, but it will no longer be able to speak. A spacecraft crossing 1 light-year at Voyager speeds would face this power decay over thousands of years. The RTG would be completely exhausted, every atom of plutonium-238 decayed, long before the spacecraft covered even a fraction of the distance. At faster speeds, the timeline compresses, but the problem remains. At 1% of light speed, the crossing takes a century. After 100 years, a plutonium-fueled RTG has lost roughly 55% of its original output. What began as 470 watts is now approximately 212 watts. Systems that were comfortable at launch are now starved. Redundant backups that were held in reserve must be activated. And the power will continue dropping for as long as the journey continues. No alternative power source solves this problem cleanly. Nuclear fission reactors, the kind that power submarines and aircraft carriers, can generate far more electricity than an RTG and can operate for decades, but they require active cooling systems, control mechanisms, and fuel assemblies that must be maintained. A fission reactor operating for a century without human intervention or resupply is well beyond anything currently demonstrated. Fusion reactors, if they existed in a practical form, might offer longer duration power, but controlled fusion has not been achieved on Earth, let alone miniaturized into a spacecraft power system. Every option either decays, wears out, or depends on technology that does not yet exist. Thermal control is coupled directly to power. In the inner solar system, spacecraft manage their temperature through a combination of passive insulation and active heaters, balancing the heat absorbed from the sun against the heat radiated into space. The engineering is well understood, but in interstellar space, the sun provides no heat. The ambient temperature is approximately 2.7 Kelvin. The spacecraft is surrounded by a cold so intense that unprotected metal becomes brittle, lubricants solidify, and battery chemistry slows to a crawl. Heaters are essential. Without them, propellant lines freeze, reaction wheels seize, electronics malfunction or stop functioning entirely. Communication systems fail, but heaters consume power, and power is the resource that is steadily disappearing. On Voyager 1, the RTGs provide not only electricity, but also waste heat, which is piped through the spacecraft to keep critical components warm. As the RTG output declines, less waste heat is available, and the spacecraft cools. Engineers must choose which systems to heat and which to allow to freeze. Each choice is a trade-off. Heat the communication system and lose a science instrument. Heat the attitude control thrusters and lose the ability to monitor the plasma environment. Every watt directed to heating is a watt not available for computation, communication, or navigation. The specific behaviors of materials at these temperatures are well documented and deeply unforgiving. Standard hydrocarbon-based lubricants, the greases and oils that allow mechanical components to move smoothly, begin to thicken significantly below minus 40 degrees Celsius and become effectively solid well before reaching the cryogenic range. Deployment mechanisms, gimbal bearings, antenna pointing actuators, anything that must move on a lubricant film, seizes if the lubricant freezes. Specialized low-temperature lubricants exist for space applications, but even these have operational flaws below which they cease to function. A spacecraft whose heaters can no longer maintain bearing temperatures above those flaws has mechanical joints that no longer move. Rubber and polymer seals behave similarly. O-rings and gaskets that maintain pressure boundaries between compartments are designed to remain flexible within a specified temperature range. Below that range, they harden, lose their ability to compress and conform to mating surfaces, and begin to crack. The Space Shuttle Challenger disaster in January of 1986 was caused in part by an O-ring that failed to seal properly at a launch temperature colder than its design specification. In interstellar space, the ambient temperature is not slightly below specification. It is hundreds of degrees below specification. Every seal on the spacecraft relies entirely on the heating system to remain above its brittle transition temperature. If the heating fails, even locally, even temporarily, the seals in that section may never recover their flexibility. A pressure boundary that was sound for decades can fail in a single cold excursion. Battery chemistry is temperature dependent as well. Lithium-ion cells, the standard for modern spacecraft energy storage, lose capacity and increase internal resistance as temperatures drop. Below approximately minus 20 degrees Celsius, most lithium-ion batteries cannot safely deliver or accept charge. If a battery bank cools below its operating range during a temporary heater outage, the spacecraft may not be able to restart the heaters using battery power, because the batteries themselves are too cold to function. This creates a potential thermal trap, a feedback loop in which cooling disables the systems needed to restore heating, and without heating, the cooling accelerates. Spacecraft engineers design against this failure mode by ensuring heater circuits have priority power access, and battery enclosures are amongst the most thermally protected areas on the vehicle. But across decades of declining power, the margins protecting against thermal traps grow thinner, and the consequences of a single miscalculation grow more severe. For a spacecraft crossing 1 light year, this thermal management problem extends for decades or centuries. The cold never relents, the heat source never recovers, and the margin between operational temperature and system failure narrows year by year. Navigation is the next system under threat, and it is perhaps the most underappreciated. In the inner solar system, spacecraft navigate using a combination of methods. The Deep Space Network, a set of large radio antenna complexes in California, Spain, and Australia, tracks spacecraft by measuring the Doppler shift of their radio signals and the time delay of two-way communications. This gives mission controllers precise information about the spacecraft's velocity and distance. Star trackers aboard the spacecraft photograph the positions of known stars and compare them to onboard star catalogs to determine the spacecraft's orientation. Accelerometers and gyroscopes provide additional data about changes in velocity and attitude. At 1 light year from Earth, the Deep Space Network cannot provide real-time tracking. The round-trip signal delay is 2 years. By the time Earth receives the spacecraft signal and calculates its position, the information is already a year out of date. Any correction commands will take another year to arrive. The spacecraft must navigate using only its onboard instruments, and those instruments must remain accurate for the entire duration of the crossing. Star trackers are the primary tool for deep space navigation. The spacecraft photographs the positions of known stars, measures the angles between them, and calculates its own position and orientation by comparing those measurements to a reference catalog. This technique, called celestial navigation, is ancient in principle. Sailors used it for millennia before the invention of modern instruments. But interstellar celestial navigation is fundamentally more demanding than anything attempted by seafarers. As the spacecraft moves, the apparent positions of stars change due to parallax. Stars that are closer appear to shift more than stars that are farther away. At 1 light year from the Sun, nearby stars have shifted noticeably against the background of more distant stars. The star catalogs loaded into the spacecraft's computer at launch are no longer perfectly accurate. The navigation software must model these parallax shifts, correcting for the spacecraft's known displacement, and recalculate star positions in real time. This requires precise knowledge of stellar distances, which are themselves subject to measurement uncertainty, and it requires onboard computers capable of performing complex trigonometric calculations reliably after years or decades of cosmic ray bombardment. A navigation error that produces a small angular deviation early in the journey compounds over distance. If the spacecraft is pointed 1/10 of a degree off course, that error translates into an offset of roughly 10 billion miles after 1 light year of travel. That is more than the distance from the Sun to Pluto. A navigation error that would be trivial in the inner solar system becomes catastrophic over interstellar distances. And the error can only be detected and corrected using onboard instruments. There is no external reference, no beacon, no ground station capable of providing a timely course fix. Gyroscopes, which provide a stable reference frame for measuring changes in orientation, are also subject to long-duration drift. Mechanical gyroscopes wear out, their bearings degrade, their spin rates change. Even laser ring gyroscopes, which have no moving parts, experience systematic errors that accumulate over time. Calibrating gyroscopes requires an external reference, and the only external reference available in interstellar space is the star field. If the star tracker degrades, the gyroscope calibration degrades with it. Each system depends on the other, and both are aging simultaneously. The structural integrity of the spacecraft is another slow-motion concern. Materials fatigue, metals subjected to repeated thermal cycling, expanding when heated by internal systems, and contracting when the heat is redirected elsewhere, develop microscopic stress fractures that grow over years. Seals between pressurized and unpressurized compartments harden and crack at cryogenic temperatures. Adhesives that bonded components at launch slowly weaken. Wiring insulation becomes brittle. Solder joints develop whiskers, tiny metallic filaments that can grow across circuit board traces and cause short circuits. These are not speculative failure modes. They are well-documented phenomena in spacecraft engineering, observed on missions lasting only years or decades. On missions within the solar system, these aging effects are managed through ground-based monitoring and, in some cases, robotic or crude servicing. The Hubble Space Telescope was serviced 5 times by space shuttle crews between 1993 and 2009, each mission replacing degraded components and extending the telescope's operational life. No interstellar spacecraft will receive a servicing mission. Whatever it launches with is everything it will ever have. Moving parts are especially vulnerable. Reaction wheels, which control the spacecraft's orientation by spinning internal flywheels, have finite bearing lives. They wear, they vibrate, they eventually fail. The Kepler Space Telescope, designed to hunt for exoplanets, lost 2 of its 4 reaction wheels during its mission, forcing a complete redesign of its observing strategy. That mission lasted 9 years. An interstellar crossing lasts decades or centuries. Reaction wheel assemblies designed for 10-year lifespans will not survive a 50-year journey without spares, and spares add mass. Valve actuators in propellant systems cycle between open and closed states, and each cycle wears the valve seat slightly. After thousands of cycles, the valve no longer seals cleanly. Propellant leaks, thrust becomes unreliable, attitude control degrades. These are problems that engineers account for in mission design by specifying the number of actuations a valve must survive. But no valve has ever been specified for a mission lasting a century. Computer memory degrades under cosmic ray exposure, as discussed in the context of Voyager 1's 2023 failure. But the problem extends beyond individual bit flips. Over decades, the cumulative radiation dose changes the physical properties of semiconductor materials. Threshold voltages shift, leakage currents increase. Transistors that once switched crisply between on and off states begin to behave ambiguously. The computer does not fail all at once. It becomes gradually less reliable. Calculations that once completed correctly now occasionally produce wrong answers. Sensor readings that once tracked physical reality now occasionally report values that are subtly incorrect. And in a system where navigation depends on precise computation, where thermal control depends on accurate sensor readings, where communication depends on reliable data encoding, gradual computational unreliability is not a minor inconvenience. It is a slow-motion systems failure that infects every function aboard the spacecraft. Redundancy is the standard engineering answer to component failure. Carry 2 of everything. If one unit fails, switch to the backup. If the backup fails, switch to the second backup. Voyager 1 was designed with extensive redundancy, and that redundancy is the reason it has survived for nearly 50 years. But redundancy is finite. Every backup unit adds mass. Every spare component occupies volume and consumes power in standby mode. And in a mission lasting decades or centuries, even deeply redundant systems eventually exhaust their reserves. The third backup fails. The fourth backup, if there is one, has been sitting in storage for so long that its own components have degraded from thermal cycling and radiation exposure. The spacecraft has been cannibalizing its own future to survive its present, and eventually, the future runs out. The compounding nature of these failures is the most dangerous aspect. Each individual degradation mode, power loss, thermal stress, navigation drift, structural fatigue, electronic erosion is survivable in isolation. Engineers can design around any one of them, but they do not occur in isolation. They occur simultaneously, and they reinforce each other. Reduced power means reduced heating. Reduced heating means wider thermal swings. Wider thermal swings mean faster material fatigue. Faster material fatigue means more frequent component failure. More frequent component failure means more switching to backup systems. More switching means faster depletion of redundancy reserves. Less redundancy means less margin for the next failure. And throughout all of this, cosmic rays continue to degrade the electronics that monitor, diagnose, and manage every other system. The spacecraft does not experience one problem at a time. It experiences a web of interacting problems that grow more entangled with every passing year. Consider a concrete example of how this compounding works. Suppose that after 30 years of flight, a cosmic ray strike damages a memory cell in the navigation computer. The error correction system detects and compensates for the fault, as it has done thousands of times before. But this particular fault occurs in a memory region that stores part of the star catalog used for celestial navigation. The corrupted entry introduces a subtle error in the calculated position of a reference star. The navigation software, using that corrupted reference alongside dozens of correct ones, produces a position fix that is slightly less accurate than it was before the strike. The error is small, perhaps a fraction of an arc-second, well within the system's tolerance margins. But the tolerance margins are not what they were at launch. 30 years of cumulative radiation have degraded the star tracker's optical sensor. Its signal-to-noise ratio has declined. It can still identify bright stars, but dimmer reference stars that it once used to improve positional accuracy are now below its detection threshold. The navigation solution relies on fewer stars than it once did, which means each individual star measurement carries more weight. The corrupted catalog entry, which would have been diluted into insignificance by a full constellation of reference stars in the early years of the mission, now has a measurable influence on the output. Meanwhile, the gyroscope that provides rotational reference between star tracker updates has developed a slow drift, imperceptible month to month, but accumulating over years. The drift was being corrected by regular recalibration against the star tracker, but the star tracker's degraded accuracy means the calibration itself carries more uncertainty. The gyroscope correction is slightly less precise. The attitude knowledge between star sightings is slightly less reliable. The pointing of the communication antenna, which depends on attitude knowledge, is slightly less accurate. The data rate achievable on the communication link, which depends on antenna pointing, drops. The amount of diagnostic information the spacecraft can transmit to Earth, should it still be within meaningful communication range, decreases. And the ability of ground controllers to detect and diagnose the navigation problem, should they ever receive the data, diminishes accordingly. No single one of these degradations is catastrophic. Each is within its own tolerance margin, albeit closer to the edge than before, but together they form a chain in which each weakened link stresses the next. The system has not failed, it has become fragile. And fragility in a machine that must endure for decades more in the same environment that created the fragility in the first place is the precursor to failure. Not the dramatic failure of a sudden explosion or a total power loss, but the quiet failure of a system that gradually loses the ability to know where it is, to point where it needs to tell anyone what is happening, and to trust its own instruments when they report that everything is fine. There is a concept in reliability engineering called the bathtub curve. It describes the failure rate of a population of components over time. Early in life, failure rates are relatively high due to manufacturing defects and infant mortality. This is the break-in period. Then failure rates drop to a low, stable level during the useful life period. Finally, failure rates rise again as components reach the end of their design life and wear-out failures begin to accumulate. The useful life period for spacecraft components is typically measured in years to a few decades. Beyond that, the curve bends upward, and failures become increasingly frequent. A spacecraft crossing 1 light-year at any achievable speed will spend most of its journey deep in the wear-out phase of the bathtub curve. It will be flying on systems that have long since exceeded their design life, maintained by whatever redundancy and repair capability it carries, without any possibility of resupply or external maintenance. It is, in engineering terms, operating beyond the edge of the known reliability envelope. No component aboard was tested for this duration. No material was validated for this many thermal cycles. No electronic system was qualified for this cumulative radiation dose. The spacecraft is in uncharted territory, and it stays there for the remainder of the crossing. This is the fundamental nature of the problem. 1 light year is not just a long distance, it is a long time. And time is what destroys machines. Not dramatically, not all at once, but quietly, cumulatively, relentlessly. A seal hardens. A wire becomes brittle. A chip absorbs 1 too many cosmic ray hits. A bearing wears past its tolerance. A valve leaks. A heater fails. A gyroscope drifts. And the spacecraft, still flying, still pointed in roughly the right direction, still carrying whatever cargo or crew it was given at launch, is a little less capable than it was the year before. And the year before that. And the year before that. The ship is a machine. Machines are built to last for a specified duration, under specified conditions. 1 light year exceeds every specification ever written. The conditions are harsher than any test environment ever constructed. The duration is longer than any qualification program ever imagined. And the ship is alone. No technician will open a panel and replace a circuit board. No supply ship will dock with fresh fuel and spare parts. No engineer will inspect the hull and patch the damage. It is a hospital with no supply shipments arriving for a century. It is a factory with no raw materials beyond what was loaded at launch. It is a navigation system that must hold its calibration across trillions of miles with no external correction. 1 light year of travel does not destroy a spacecraft in a single catastrophic event. It wears the spacecraft down. It drains its power. It erodes its shielding. It degrades its electronics. It stiffens its joints and fogs its sensors and stretches its communication link until the link is measured in years rather than seconds. Every system aboard the spacecraft is on a clock, and none of those clocks were set for the duration of the crossing. And here is the detail that makes all of this worse. 1 light year is not the journey. 1 light year is not the distance to the nearest star. It is not the distance to a destination, a harbour, a new world, or even a point of particular interest. It is less than a quarter of the distance to Proxima Centauri, the closest star beyond our own sun. Everything described so far, the speed problem, the environmental hazards, the communication isolation, the power decay, the thermal stress, the navigation challenge, the slow-motion aging of every system aboard the ship, all of it applies to the first light year. And after the first light year, there are still more than 3 light years remaining before the spacecraft reaches even the nearest star. Every hazard multiplies, every degradation continues, every clock keeps ticking, and the ship, already worn, already weakened, already operating far beyond its design life, must endure it all again and again and again, 4 times over at minimum, before it arrives anywhere at all. That is the context in which 1 light year must be understood, not as the whole journey, but as the first fraction of one. The opening act of a crossing so long and so demanding that even this single fraction is enough to challenge the limits of everything humanity has ever built. Everything up to now has been about 1 light year in isolation. The speed required to cross it, the environment encountered during the crossing, the slow degradation of every system aboard a spacecraft as time and distance take their toll. 1 light year treated as a journey in itself, examined in its own terms, measured against its own hazards. And even in isolation, the picture is severe. The 5.88 trillion miles of gas, dust, radiation, cold, and darkness crossed by a machine that ages faster than anyone planned for, powered by a fuel that decays by the laws of physics, communicating with Earth on a delay so long that every message is a monologue sent into the past. But 1 light year is not a journey in itself. It is a fraction of one. And understanding what that fraction means is the final piece of this story. The nearest star to our solar system is Proxima Centauri. It is a small red dwarf star, about 12% the mass of our Sun and roughly 14% of its diameter. It emits less than 1% of the Sun's luminosity. If you replace the Sun with Proxima Centauri, the Earth would freeze. It is not visible to the naked eye from anywhere on the planet. You need a telescope to see it at all, and it is the closest star there is. Proxima Centauri sits at a distance of 4.24 light years from the Sun. The European Space Agency's Gaia mission has refined this measurement to extraordinary precision, pinning the distance at 4.2465 light years. That is approximately 25 trillion miles, roughly 40 trillion kilometers. It is part of a triple star system called Alpha Centauri. The other 2 members, Alpha Centauri A and Alpha Centauri B, are Sun-like stars that orbit each other at a distance of about 4.37 light years from Earth. Proxima Centauri orbits this pair at a much greater distance, taking roughly 550,000 years to complete a single orbit. It is the closest of the 3 to us, which is why it carries the name Proxima, from the Latin word for nearest. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri. They named it Proxima Centauri b, and it is roughly Earth-sized, orbiting within what might be the habitable zone, the range of distances where liquid water could theoretically exist on a planet's surface. In 2025, a second planet, Proxima Centauri d, was independently confirmed. It is much smaller, approximately 1/4 the mass of Earth, orbiting very close to the star with a period of just 5.1 days. The system is real. The planets are real. The destination, if humanity ever attempts to reach another star, is not hypothetical. But the distance is 4.24 light years, not 1. Take everything described in the previous 3 parts and multiply it. Not by 2, not by 3, by more than 4. Every hazard, every degradation, every compounding failure mode that applies to 1 light year applies for more than 4 times as long to reach the nearest star. At Voyager 1 speed, 1 light year takes approximately 17,600 years. Proxima Centauri takes approximately 73,000 years. The entire span of modern human existence, from the earliest cave paintings to the present day, fits inside that number with room to spare. Multiple ice ages have come and gone in less time. Human languages have been born, evolved, branched into families, and gone extinct many times over in 73,000 years. And Voyager 1 would still be coasting through the interstellar medium, still decelerating imperceptibly under the faint gravitational pull of distant stars, still not there. At 1% of light speed, 1 light year takes a century. Proxima Centauri takes 424 years. That is longer than the entire history of the United States, longer than the span from the Mayflower's voyage to the present day. A spacecraft launched at 1% of light speed during the reign of Queen Elizabeth I would be arriving at Proxima Centauri roughly now. Every system aboard that spacecraft would need to have survived for more than 4 centuries without resupply, without maintenance from outside, without any component that was not carried from launch. At 10% of light speed, 1 light year takes a decade. Proxima Centauri takes approximately 42 years. That is the most optimistic scenario that involves anything resembling proven physics. And even that requires propulsion technology that does not yet exist. 42 years is a significant fraction of a human lifetime. A crew member who launched at 30 would arrive at 72, having spent their entire adult life inside a spacecraft that is aging at least as fast as they are. The power problem scales directly with distance. A plutonium-238 RTG that has lost 55% of its output after 1 century of travel has lost roughly 80% after 2 centuries, and more than 90% after 3. The exponential decay curve is merciless. By the time a slow-traveling spacecraft reaches the halfway point to Proxima Centauri, its original power source has been functionally dead for thousands of years. Even at faster speeds, the power budget is agonizingly tight. At 10% of light speed, 42 years of decay costs roughly 30% of the original RTG output. Manageable, perhaps with careful engineering, but there is no margin for error. Every watt matters. Every heater that runs longer than planned, every computer that draws more current than expected, every system that cannot be shut down because it is critical eats into a budget that only shrinks. The radiation exposure accumulated over 4.24 light years is more than 4 times what accumulates over 1. Cosmic ray dose is roughly proportional to time in interstellar space. A crossing at 10% of light speed exposes the spacecraft and crew to 42 years of unshielded galactic cosmic ray bombardment. That is a cumulative dose that current space medicine regards as deeply concerning, even with optimistic assumptions about shielding effectiveness. At slower speeds, the exposure grows proportionally. A century-long crossing produces a century of dose accumulation. 4 centuries. 4 centuries of dose. The cancer risk climbs. The electronic degradation compounds. The DNA damage accumulates faster than cellular repair mechanisms can fix it. And across generations, if the journey spans generations, the genetic consequences become a population-level concern. The dust erosion also scales with distance. 4.24 times as many miles means 4.24 times as many dust grain impacts. The leading face of the spacecraft that was merely pitted after 1 light year is significantly eroded after 4. Shielding layers that provided adequate protection over 1 light year may be worn through after 2 or 3. And if the shielding fails, the structural hull is exposed to direct impacts from particles carrying the kinetic energy of small explosives. Navigation errors compound over distance. A 1/10 of a degree angular error after 1 light year produces an offset of roughly 10 billion miles. After 4.24 light years, the same error produces an offset of approximately 42 billion miles. That is the difference between arriving in the Proxima Centauri system and missing it by a distance comparable to the radius of the solar system. At interstellar speeds, a missed target means the spacecraft flies past the destination and continues into the void. There is no turning around. There is no second approach. The spacecraft either navigates with extraordinary precision across the full distance, or it does not arrive. And here's a detail that sharpens the entire picture. Voyager 1, the most distant human-made object, the spacecraft that has been flying longer and farther than anything ever built, is approaching a milestone that puts all of these distances into brutal perspective. In late 2026, Voyager 1 will reach 1 light day from Earth. 1 light day. The distance light travels in 24 hours, approximately 16 billion miles or 26 billion kilometers. After nearly 50 years of continuous flight at 38,000 miles per hour, Voyager 1 will have covered a distance that light crosses in a single day. 1 light year is 365.25 light days. Voyager 1 has spent almost 50 years reaching 1 light day. At that rate, reaching 1 light year would take approximately 17,600 years. And reaching Proxima Centauri, 4.24 light years away, would take approximately 73,000 years. The ratio is staggering and it resists intuition. People hear that Voyager 1 has been traveling for nearly 5 decades and has reached interstellar space, and they imagine that interstellar travel is, if not easy, at least underway. It is not. Voyager 1 has crossed 1 light day. The nearest star is at roughly 1,500 light days. Voyager 1 is not 1% of the way to Proxima Centauri. It is not 1/10 of 1%. If the journey to Proxima Centauri were a road stretching from New York to Los Angeles, Voyager 1 would have traveled approximately 1.6 miles. Still within the city, still visible from the starting point, barely out the door. This is not a failure of Voyager 1. Voyager 1 is one of the greatest engineering achievements in human history. It has functioned for nearly 5 decades in the most hostile environment imaginable, returning data from distances that seemed impossibly remote when it launched. It has survived cosmic ray hits, computer failures, power decay, and thermal extremes that would have destroyed lesser machines. It is a triumph of design, engineering, and operational skill. And it has barely begun the journey to the nearest star. This is the scale of the problem. Not the scale of the universe in the abstract, not the distances measured on a classroom poster, but the scale measured in hardware, in fuel, in watts of power and years of life and miles of travel by the actual fastest interstellar vehicle humans have ever built. The gap between what we have achieved and what the stars require is not a gap that better engineering will close incrementally. It is a gap of a different magnitude entirely. A gap that demands propulsion systems and power systems and life support systems that do not merely improve on current technology, but transform it. And even the most ambitious proposals only partially close that gap. The breakthrough starshot concept, which would accelerate a gram-scale probe to 20% of light speed using a ground-based laser array, would reach Proxima Centauri in approximately 21 years. That is a breathtaking number compared to Voyager 1's 73,000. But the probe would weigh a gram. It would carry no crew, no life support, no meaningful scientific payload beyond a few miniature sensors. It could not slow down at the destination. It would pass through the Proxima Centauri system at 60 million meters per second. collecting data for a few hours before continuing into the interstellar medium forever. And even this minimal concept, as noted earlier, has largely stalled as an engineering program. The physics is sound. The funding, the hardware, and the political will are not there. Nuclear pulse propulsion, the Orion concept, could theoretically send a large crewed vehicle to Proxima Centauri at several percent of light speed, arriving in roughly a century or two. But it requires thousands of nuclear detonations in space. A political impossibility under current international law. Fusion drives could potentially do better, but fusion propulsion does not exist as a technology. Antimatter drives could do better still, but antimatter production is measured in nanograms per year. Each concept improves on the last, and each is further from reality than the one before it. The honest assessment, based on everything we know about current technology, near-future engineering, and the physics of interstellar distance, is that crossing 1 light year is already beyond the operational envelope of any machine humanity has ever built, and reaching the nearest star requires crossing more than 4 of them. This is not an argument against trying. It is an argument for understanding what trying means. It means that interstellar travel, even to the nearest star, is not a faster version of planetary exploration. It is a categorically different kind of endeavor. The missions humanity has flown within the solar system, to the moon, to Mars, to Jupiter and Saturn and Pluto, were difficult and dangerous and expensive. They required extraordinary engineering and courage. But they shared a common feature. They were finite. They had timelines measured in months or years. They maintained communication with Earth in seconds or hours. They operated within the protective influence of the sun's energy and, for the inner planets, within the partial shelter of Earth's magnetic environment. They could be monitored, adjusted, and in some cases, rescued. An interstellar crossing has none of these features. It is measured in decades or centuries. Communication is measured in years. The sun's energy is absent. The magnetic environment is the open galaxy, unshielded and unforgiving. Rescue is impossible. Resupply is impossible. Every component, every calorie, every watt of power must be carried from launch or generated on board without external input. The spacecraft is not an extension of Earth. It is a replacement for Earth, a closed system, isolated in every sense, that must function independently for longer than any machine has ever functioned. 1 light year is the first mile of that road, and even the first mile is enough to reveal the full weight of what lies ahead. The communication delay at 1 light year is 1 year. At Proxima Centauri, it is 4.24 years. The difference is quantitative, not qualitative. The isolation is already complete at 1 light year. The spacecraft is already beyond any timely help. Every additional light year simply deepens the silence. The power decay at 1 light year depends on speed, but any currently possible speed, it is significant. At Proxima Centauri, it is 4 times worse. The radiation dose at 1 light year is already beyond anything permitted by current health standards for astronauts. At Proxima Centauri, it is 4 times higher. The dust erosion, the thermal stress, the navigation challenge, the structural fatigue, every single hazard described tonight scales with distance, and the distance to the nearest star is more than 4 times the distance we have been examining. 1 light year is enough to prove all of this. It is enough distance to show that communication becomes a monologue, that power fades by the laws of nuclear physics, that electronics degrade under cosmic ray bombardment. that mechanical systems age beyond their design life. That navigation requires precision maintained across trillions of miles with no external correction. 1 light-year is enough to demonstrate that interstellar space is not a void to glide through, but a medium to endure. It is enough to reveal that the real obstacles to reaching another star are not the obstacles of getting off the ground, not the engineering of launch vehicles and orbital mechanics, but the obstacles of lasting long enough for the distance to be crossed. We sometimes speak of space travel as though the hard part is the launch, getting off the planet, reaching orbit, escaping Earth's gravity well, and for missions within the solar system, that is largely true. The energy required to escape Earth's gravity is the single largest expenditure of any planetary mission. Once you are in orbit, the rest is patience, precision, and trajectory management. But for interstellar travel, the launch is the easiest part. It is the crossing that breaks you. The months and years and decades of continuous operation in an environment that erodes everything you brought. The slow draining of power, the steady accumulation of radiation damage, the widening communication gap that eventually becomes permanent silence, the mechanical aging that no amount of redundancy can indefinitely prevent, the navigation challenge that compounds with every passing year, all of it unfolding in darkness, far from any star, with no waypoint, no harbor, no destination closer than the stars themselves, which are still light years ahead. 1 light-year is the distance that makes all of this visible. It is the first threshold where the true nature of interstellar travel reveals itself. Below 1 light-year, you are still in the solar neighborhood, still within hailing distance of the sun in some meaningful sense, still within the gravitational sphere that defines our stellar home. Beyond 1 light-year, you are in the interstellar medium, genuinely and completely. The sun is a star among stars. Earth is undetectable. Home is a memory carried in the databanks, and, if there is a crew, in human minds that grow older with every passing year. And 1 light-year is only the beginning. Beyond it, the distances only grow. Barnard's star is approximately 6 light-years away. Ross 128 is about 11 light-years. Tau Ceti is nearly 12. The stars that might harbour habitable worlds, the ones with confirmed planets in promising orbits, are scattered across a volume of space measured in tens and hundreds of light-years. Each additional light-year is another iteration of the same ordeal. Another decade or century of power decay, radiation exposure, dust erosion, thermal stress, and navigation drift. Another stretch of darkness with no features and no refuge. The conclusion is not that interstellar travel is impossible. The physics does not forbid it. Nothing in the laws of nature says a spacecraft cannot cross 1 light-year, or 4, or 40. The speed of light is a limit, not a wall. Below it, travel is permitted. The energy requirements are enormous but finite. The engineering challenges are severe but conceivable. Human beings have consistently achieved things that earlier generations considered impossible, and there is no reason to believe the pattern will end. But the conclusion is that 1 light-year is already far harder than most people imagine. It is not a unit on a chart. It is not a number to be casually inserted between the words only and away. It is a physical distance through a physical medium, crossed by a physical machine, over a physical duration, and every one of those physical realities is hostile to the survival of the machine and everything it carries. 1 light-year does not feel like a step. It feels like a test of power, of communication, of navigation, of structural endurance, of thermal survival, of radiation tolerance, of the ability of a machine to function far beyond anything it was designed to endure. Alone, in the dark, with no help coming and no destination in sight. For light, 1 light year is 1 year. Effortless. Instantaneous in the subjective experience of a photon, if photons could experience anything. A beam of light departs the sun and reaches the 1 light year mark without aging, without degrading, without losing a single watt of energy to the crossing itself. Light does not endure the interstellar medium. It passes through it at the maximum speed the universe allows, unchanged and undiminished. For a spacecraft, 1 light year is a different thing entirely. It is decades at best, and millennia at worst. It is a communication link stretched so thin it becomes silence. It is a power supply bleeding out in slow motion. It is electronics crumbling under invisible particle fire. It is a hull being sandblasted by grains of dust that carry the energy of explosives. It is a navigation system trying to hold a course across trillions of miles with no external reference, no correction signal, no ground truth. It is a machine enduring conditions it was never built to survive. For a duration it was never designed to reach, in an environment that gives nothing back. 1 light year is the distance that separates what space travel is from what interstellar travel would be. Everything humanity has done in space so far, every mission, every station, every rover, every probe, has operated within 1 light day of the sun. Most of it has operated within 1 light hour. The farthest we have ever reached is 1 light day, and that single light day consumed 50 years and every ounce of engineering brilliance we could bring to bear. 1 light year is 365 times farther, and the nearest star is 4 times farther than that. This is the truth that the phrase 1 light year conceals behind its simplicity. It sounds small because the universe is large. It sounds routine because astronomers use it casually. It sounds manageable because it is only 1, and numbers close to 1 feel approachable. But behind the word, behind the number, is a crossing so vast, so hostile, and so demanding that it transforms the meaning of space travel entirely. It is no longer a mission. It is a survival problem measured not in days or weeks, but in decades and centuries, fought not against a single dramatic threat, but against the quiet, compounding degradation of everything the spacecraft needs to stay alive. 1 light year is not the beginning of the stars. It is not the first rung on a ladder to the galaxy. It is not a stepping stone. It is the first proof. The first hard, undeniable evidence that the distance between the stars is not merely large, but actively, physically hostile to anything that tries to cross it. It is the point where the numbers stop being abstract and start being real, where the unit on the chart becomes a journey through gas, dust, radiation, cold, silence, and time, where the difference between light's crossing and a spacecraft's crossing becomes not a ratio, but a verdict. The stars are beautiful. They scatter across the night sky in patterns that have guided sailors, inspired poets, and anchored civilizations for as long as humans have looked upward. They feel close because they are visible. They feel reachable because we can name them, catalogue them, measure their distances, and study their light. But between us and every one of them lies an ocean that has no islands, no currents, no wind, and no shore. An ocean measured in light years, where every single light year is an ordeal unto itself, and the nearest shore is more than 4 of them away. 1 light year, 5.88 trillion miles. The distance light covers in 12 months, moving at 186,000 miles per second. For a photon, it is nothing. For a spacecraft, it is everything. And it is only the first step on a staircase where you cannot see the top. Sleep well tonight. And the next time someone tells you the nearest star is only 4.2 light years away, remember what you now know about the first one. Good night.